Hi everyone, my name is Quanquan, and today I'll be talking about our work on near-optimal distributed implementations of dynamic algorithms for symmetry breaking problems. This is joint work with Shiri, Antaki, and Shay Solomon at Tel Aviv University. To start, a vast majority of earlier work on graph algorithms focused on the sequential centralized setting. Furthermore, these works usually considered static algorithms where the solution to a problem is recomputed each time from scratch. Often, these algorithms must be run on very large networks. We've included here on the slide some examples of publicly available datasets of several large social networks. You can see the number of edges range from millions to 100 billion edges, and these sizes are only for publicly available datasets. The private network graphs collected by some companies could be even larger, up to trillions of edges. Moreover, real-world networks are often dynamically changing, with new edges being inserted and deleted every second. Social networks, for example, host new connections every second. These changes change the topology of the graph, which means that static algorithms would often need to be rerun several times to obtain accurate statistics. On very large graphs with billions of edges, even linear time static algorithms are too expensive to be rerun many times as the graph changes. This then naturally motivates the study of dynamic graph algorithms, which are also traditionally studied in the sequential centralized setting. Unlike static algorithms, dynamic algorithms recompute part of the solution after each update, instead of recomputing the entire solution from scratch as in static algorithms. This allows such algorithms to spend less time computing a solution compared to rerunning the static algorithm multiple times. Thus, the quality measure we care about for dynamic algorithms is the update time, or the time required to compute a solution after updates. The goal of sequential centralized dynamic algorithms is to minimize this update time. And here's an example of a very simple dynamic maximal independent set algorithm. Suppose we have an edge deletion indicated in red here between U and V. After we delete the edge, U checks all its neighbors to see whether it has any neighbors in the MIS. U in this example doesn't, so we add it to the MIS. For an edge insertion, if the insertion occurs between two nodes in the MIS, here in this example, the insertion is between U and W, we remove one of them from the MIS, W here, which can cause one of its neighbors, X here, to be added. One nice aspect of the sequential centralized model is that we can access all of the vertices on one machine. However, given today's large graphs with billions or even trillions of edges, it often requires too much memory and time to process the graph sequentially on only one machine. Naturally, the next step is to then split the large graph among many different processors or machines, where each node is a processor or machine, and edges are communication links between the machines. Nodes can send messages to each other via the edges. And in this paper, we consider the multicast model, where nodes can choose to send the same or different messages to some or all neighbors. Nodes can use multiple rounds of communication to send messages, where in each round, they can send messages to the same or different neighbors. The message complexity of a distributed algorithm is the number of messages sent in total over the entire course of the algorithm. In this paper, we consider the congest model, where messages have O of log n size. A problem with sending too many messages is that it can overwhelm the network bandwidth, and I'll talk a bit more about this problem later on. Another complexity measure we care about is the round complexity, which is defined as the number of rounds the algorithm uses. One problem with having too many rounds is that it takes too long for the algorithm to compute a solution. And it can also result in the algorithm sending too many messages. Distributed networks can also be dynamic, where edges are added and deleted from the network. Such dynamic changes also change the communication topology of the network. On these dynamic distributed networks, the grand prize we seek to obtain for dynamic distributed algorithms is to have message complexity that matches the update time of the best known sequential centralized algorithm, while also maintaining O of 1 round complexity. Furthermore, an even better characteristic which we achieve in our paper is that the algorithm is robust against adaptive adversaries. Adaptive adversaries are defined to be adversaries which determine the next update or the edge changes in the graph after they see all of the previous outputs of the algorithm. Deterministic algorithms are naturally robust against adaptive adversaries, and all of the algorithms presented in our paper are deterministic. A number of previous works have studied dynamic distributed algorithms, but most have focused on minimizing round complexity. These works operate in the setting of dynamically changing distributed networks. And some very recent works have also studied simultaneously handling many concurrent updates. However, the algorithms in these works operate by sending messages to all neighbors via broadcasts. This means that the number of messages required by these algorithms is at least omega of delta, where delta is the maximum degree in the graph. This also means that the number of messages sent can be as large as omega of m for sparse graphs. Perhaps surprisingly, very few previous works consider the number of messages sent by the algorithm after dynamic updates as a complexity measure. There are many practical real-world situations where few messages may be required. Some examples include systems with poor wireless connections, an oversaturated network where many independent agents are on the same network, or a mobile data network in a poorly connected area. Our work focuses on using multicasts for nodes to send messages to specific subsets of their neighbors, not all of their neighbors. A few works have studied message complexity for certain problems. Asadi, Onak, Schieber, and Solomon gave a O of m to the 3/4 amortized message complexity and O of 1 round algorithm for MIS. Peleg and Solomon gave an O of alpha over epsilon worst case message complexity and O of 1 round algorithm for 1 plus epsilon maximum cardinality matching. Here, alpha is a graph property known as arboricity, which is a measure of graph local sparsity. Alpha could actually be quite large. It could be as large as square root of m in general graphs. Finally, Kaplan and Solomon gave an O of log n amortized messages low out degree orientation algorithm in O of 1 amortized rounds for constant alpha. In light of these previous works, and to reiterate what we said before we move on to our main results, the gold standard for dynamic distributed algorithms is that the message complexity matches the update time of the best known sequential centralized algorithm while maintaining O of 1 round complexity. There are a number of challenges for adapting centralized dynamic graph algorithms to the distributed setting. First, it is difficult for all nodes to determine the number of edges in the graph if updates on disconnected components of the graph occur. Because the edges represent communication links, two disconnected components have no way to communicate with each other how many edges are in their respective components. This is an issue because many algorithms use such information. Second, Many centralized algorithms perform global restarts where a large portion of the graph recomputes some information. Such a global restart in the distributed setting would mean that information must be propagated throughout much of the network, which could result in both high round and also high message complexity. Here's an example. Suppose the restart starts from this yellow node shown in this graph, and the restart propagates to the neighbors of the node and to their neighbors and so on until it propagates to a large part of the network. This takes diameter number of rounds, and while a global restart may not reach every single node in the network, it could still take omega of the diameter number of rounds. The solution to these challenges is to consider information from the partial local neighborhood, not the entire graph. Using the local neighborhood reduces the round complexity, and using a portion of the local neighborhood or the partial local neighborhood reduces the message complexity. We study a number of symmetry breaking graph problems in our paper, including delta+1 coloring, maximal matching, 3/2 approximate maximum matching, and maximal independent set. And our algorithms achieve this grand prize up to polylog factors in the message complexity as well as the rounds. Specifically, for delta+1 vertex coloring and maximal matching, we show dynamic distributed algorithms using O of square root of m messages and O of 1 rounds, both worst case, and the message complexity exactly matches the update time of the best known sequential centralized algorithms. Both of these results use dynamic edge orientation techniques, where we maintain edge orientations dynamically such that the edges are approximately oriented from nodes with smaller degree to their larger degree neighbors. You can refer to our paper for specific details about these algorithms. We also give an O of square root of m amortized messages O of log delta worst case round algorithm for 3/2 maximum matching using the high degree, low degree partitioning technique with surrogates formulated first by Neyman and Solomon. While in the centralized algorithm, the number of edges is always known, it is not known in the distributed setting, as I mentioned before. We show in our paper that using the surrogates also allows us to do a low degree, high degree partitioning of vertices by looking at only a partial 2-hop neighborhood of each vertex. This also matches the best known sequential centralized algorithm in message complexity, and the number of rounds obtained is a polylog factor from O of 1. And to find out more about this algorithm, please also refer to our paper. Finally, the rest of this talk will focus on our main result for maximal independent set, or MIS, where we give an algorithm that achieves O of m to the 2/3 log squared n amortized messages and O of log squared n amortized rounds using a high degree and low degree partitioning. This partitioning is obtained by using only a local 6-hop neighborhood. The other main components of our algorithm are our use of a small diameter static algorithm for high degree vertices and a dynamic MIS algorithm for low degree vertices. This matches the best known sequential centralized algorithms by up to polylog n factors. A maximal independent set is defined as a maximal set of vertices where no two vertices in the set are neighboring. Edge insertions may violate the independence of the vertices as shown in this example, where two vertices that are adjacent to each other are both in the MIS after this edge insertion. While edge deletions may violate maximality, as you can see in this example, where after the edge deletion indicated in red, and other new vertex is added to the MIS, as shown by this yellow vertex here. As mentioned previously, Asadi, Onak, Schieber, and Solomon provide a deterministic dynamic distributed MIS algorithm that uses O of m to the 3/4 amortized messages and O of 1 amortized rounds. However, their algorithm uses one crucial characteristic of the graph, which is that the graph remains connected throughout all the updates. Compared to this previous result, we improve the message complexity polynomially while only paying a polylog n factor in the number of rounds. And most importantly, we obtain our result without making any connectivity assumptions. Our result builds upon the sequential centralized dynamic MIS algorithm of Gupta and Khan. Their algorithm partitions the nodes into high degree and low degree nodes, where the cutoff for this partition is at m to the 2/3. MIS membership priority is given to low degree nodes, so the nodes with degree less than m to the 2/3. And this means that a low degree node will add itself to the MIS if it has no other low degree neighbors in the MIS. High degree nodes are only added to the MIS after processing the low degree nodes, and they are added if they have no neighbors in the MIS. Low degree nodes, which enter or exit the MIS, can cause many high degree nodes to either enter or leave the MIS. Gupta and Khan handles this by performing a global restart after every edge update, which finds a new MIS among all high degree nodes in the graph. There are two main challenges we need to solve in distributing the Gupta and Khan algorithm. First of all, we need to determine the high degree and low degree nodes as m changes and when the graph may be disconnected. When the graph is disconnected, as I mentioned before, nodes have no way to find out the number of edges in the graph because they cannot communicate across disconnected components. This is in contrast to the case when the graph is connected throughout all updates. In that case, the nodes can find out the number of edges in the graph through a broadcast to the entire network. However, this assumption is not quite realistic for real-world networks. The second challenge is how do high-degree nodes compute whether they need to enter the MIS in a small number of rounds and messages. A global restart, which looks at all high-degree nodes, takes too many rounds. In fact, it can take up to diameter number of rounds in the distributed model. So for high diameter graphs like road networks, that is too expensive. So now I'm going to describe our distributed algorithm, and I'll start with a very high level description. Our distributed algorithms works in the following way. As in Gupta and Khan, low degree vertices have priority in entering the MIS. On an edge insertion, an endpoint removes itself from the MIS if the edge insertion violates independence. In this example, one of the endpoints of the insertion removes itself. After the vertex removes itself, its neighbors are added to the MIS if maximality is violated. Low degree neighbors have priority in adding themselves to the MIS. After the low degree neighbors have added themselves to the MIS, potentially a large number of high degree vertices may need to remove themselves from the MIS. In this example, one high degree node needed to remove itself from the MIS, so we remove it. And finally, if there are any remaining high degree vertices that need to enter the MIS, they proceed to do so. But these high degree nodes need to determine an MIS in the induced subgraph amongst themselves. And we'll talk a bit later about how they decide which ones will enter the MIS. On an edge deletion, maximality may be violated. And so neighbors are added to the MIS if possible, giving priority to low degree nodes. In this example, a high degree node is added to the MIS since no additional low degree nodes may be added. As in the case for insertions, there are potentially many high degree nodes that may be added or removed from the MIS as a result of a single low degree node entering or leaving the MIS. There are some important things to consider about the algorithm I just described, so let me mention them now. First, edge insertions or deletions may cause nodes to switch their degree designation. So low degree nodes may become high degree and vice versa, many times throughout the course of the entire algorithm over many updates. Then when an edge update causes a low degree node to enter or leave the MIS, the dynamic algorithm of AOSS 18 is run on the low degree node to determine its set of low degree neighbors to add to the MIS. While several low degree nodes may enter the MIS as a result of an edge update, at most one low degree node ever leaves due to an update, specifically due to an edge insertion. Low degree nodes that enter the MIS can cause many high degree nodes to leave, as we mentioned before. And similarly, low degree nodes that leave the MIS can cause many high degree nodes to enter. While Gupta and Khan perform a global restart at every update step among all high degree nodes to determine the set that enters or leaves the MIS, what we do instead is that we perform a local restart on the set of high degree nodes in the local neighborhood only when needed. And we will give specific details on this procedure in the next few slides. Tying our algorithm back to the challenges, this entire algorithm hinges on the fact that we need to know which nodes are high degree and which are low degree, which is a non-trivial hurdle to overcome. And furthermore, we need to know when nodes become high degree from low degree and vice versa. And we solved the second challenge I mentioned before by performing a local restart only when necessary, compared to the Gupta and Khan algorithm, which performs a global restart in the centralized model among all high degree nodes after every update step. Now we'll give more details on how we solve challenge 1, which is how to determine low degree, high degree designations. To solve challenge 1, we initialize a counter PV for every node V, which starts with value 1, assuming that we start with an empty graph. All vertices are initially low degree, and when the degree of any vertex exceeds 2 PV due to edge insertions, for example, vertex V in this diagram, where vertex V exceeds degree 2, the vertex then makes itself high degree. The node V then updates PV to equal its current degree when it becomes low degree again. This procedure may result in too many high degree nodes. Importantly, we don't deal with them now. We make high degree nodes low degree again when we perform a local restart. And as I mentioned before, local restarts are only performed when we need to determine which high degree nodes need to enter the MIS. The rest of the procedure then boils down to solving challenge 2, which is determining the set of high degree nodes that need to enter the MIS. Suppose in the example, the highlighted yellow nodes are in the MIS. On an edge insertion, a low degree neighbor may need to leave the MIS. In this example, U or its neighbor must leave the MIS. So suppose U left the MIS, then there may be many high degree neighbors that want to enter the MIS. In this example, X, Y, and V no longer have any neighbors in the MIS, so they all want to enter. But of course, not all of them can enter because there are some edges connecting them. So they must determine an MIS in their induced neighborhood, which would tell you which ones will be added to the MIS. Before we run the algorithm for determining which ones will enter, we must go back and solve challenge 1 again. Since some of these quote-unquote high-degree nodes may actually be low-degree, recall from before, we haven't actually yet dealt with these high-degree vertices, which have become low-degree due to deletions. So to determine the set of high-degree vertices that have become low-degree, we first determine the set of degrees of all nodes in the one-hop neighborhood of the low-degree vertex that we initially removed from the MIS. In this example, that vertex is U, and the sum of the degrees of its one-hop neighborhood is 12. Then any vertex with degree less than the sum raised to the 2/3 becomes low-degree. In this example, x and y both have less than 12 to the 2/3 degree, so they become low degree. Vertices which became low degree have priority in joining the MIS. And so both x and y in this diagram join the MIS. Suppose instead, x and y remain high degree after doing our local restart. We run a static distributed MIS algorithm on the induced subgraph of high-degree nodes in the local neighborhood of U. The specific algorithm we use is the static algorithm of Sensor-Hello, Parter, and Schwartzman, which operates in polylog n rounds on small diameter graphs. As you can see in this example, this induced subgraph has small diameter, and in fact, the diameters of the subgraphs we look at in our algorithm are at most 6. Specifically, their algorithm requires a leader, and so in our case, the low degree node, which removed itself from the MIS initially, is the leader. In this example, U becomes the leader. Because their algorithm is deterministic, it requires all the nodes participating in the algorithm to communicate information with the leader over several polylog rounds. This is the reason why small diameter is important in order to obtain polylog and total rounds for the entire algorithm. Running their algorithm in this example, we pick V to join the MIS. The message complexity of our algorithm is O of m to the 2/3 log squared n amortized, where m is the average number of edges over all updates. We also show the same result for maximum number of edges. This message complexity is due to the fact that low degree vertices have degree O of m to the 2/3. And there are at most O of m to the 2/3 edges in the local high degree neighborhood. Finally, this bound is amortized because the local restarts, which determine whether any high degree nodes become low degree, is amortized. The log squared n factor comes from the number of rounds our algorithm runs. Our algorithm requires O of log squared n rounds because CPS20, the static algorithm that we use for finding the MIS among the high degree neighbors, requires O of log squared n rounds on constant diameter graphs. As in this example here, and as I mentioned before, we only ever run our algorithm on local subgraphs with diameter at most 6. The amortization in the bound comes from running AOSS 18 on the low degree neighbors. And this algorithm requires O of 1 amortized rounds. And that concludes the technical portion of this presentation. So to conclude with some final thoughts, we initialize a formal study of message-efficient distributed dynamic algorithms. We show a number of results that achieve the grand prize up to O of log squared n factor or smaller. In obtaining these results, we solve several rather general challenges, such as an unknown number of edges or how to perform restarts efficiently and locally. There are a number of questions that are interesting as a result of our study, and we think that these questions will be interesting directions to explore in future work. And so these questions include, can the techniques in our paper be generalized for a wide class of dynamic distributed algorithms? Can we achieve worst case bounds, especially for the number of rounds for MIS? Furthermore, can we also get rid of the O of log squared n factors, especially in round complexity for MIS? Recall the log squared n factors were a result of running the static algorithm, so can we perhaps use another technique to get rid of them? Can our algorithms be modified to handle multiple concurrent updates while maintaining low message complexity? And finally, is there a general purpose compiler which takes a centralized dynamic algorithm and outputs a message efficient distributed dynamic algorithm? So this is a very general question, but we think it would be very interesting if we can provide such a framework for turning centralized dynamic algorithms to dynamic distributed algorithms where the message complexity equals the update time and we maintain O of 1 rounds. This is possibly the way to achieve the grant prize. And with this, I conclude our presentation. Please check out our paper, and we're happy to take any questions over email.